Can you hear me? Yeah, cool. So today is the first practicum, and I hope that you all have the link. It's uploaded in India's. So what you're supposed to do is just read through and try to solve the problems. So the problems are not exactly given like to solve the whole thing. But so basically there are some dots here. Sorry. So dots, and then you have to fill the correct codes for those places. For example, I can show you for one. How does it look like? For example, like this. Read through the descriptions of the questions so that you can get understanding of what actually is given and what you are supposed to solve. And is there anything? Yeah, this is not to be graded. This is for practice. And yes, as I said, that you work on your own, and then we'll go over the solutions probably in the last 20 minutes or so. And yeah, remember to make a copy of this notebook, because if you try to change on the just like clicking a link, and then your changes won't be saved. So do it. And yeah, I guess if there's any problem, then yeah, you can ask me. Yeah. Hopefully that's not difficult to understand, but yeah. Sorry, do you need me to explain the questions for you? I mean, if you suggest so that I can do. Or is it? Okay. Okay. So the first question here is solving XOR task with single perceptron. I'm hoping that you guys have been attending Professor's newest class. So if you were in the first class, he already went over through this. So what does that mean is like you will try to solve the XOR problem and see if it's really linearly separable also. And yeah, so go through this. You're giving one neuron, and one neurons are basically, yes, takes two binary input values and return a binary output, so either 0 or 1. And the idea is to try to solve the XOR problem, which has an input of these 4. So whenever they are similar, so the A and B are the inputs. Whenever they are similar, for example, A is also 0, B is also 0, and A is 1, B 1, and they give the output as 0. And if one of them is 1, then the output is 1. And yeah, so try to solve the problem with single perceptron. And we'll see what happens in the end of this, and then move to the next question. Please let me know if you have any problems, and we can move over to the next question in 15 minutes.
You can also change the setting.
Change the setting, yes.
That I didn't know. If I do, yeah.
I didn't mess with it, but we should have especially.
Feel like I don't. But it's like, yeah, you need to not prepare. I mean, it's just all like. I don't have anything to also.
But usually it's just.
Yeah, sure. So you're saying it's like this, like you remember you put the hard side.
Should not be. But he used to.
Sorry, did you guys finish this already? No? Do you want me to go over to the next ones? Because I think did any of you finish? Okay, so I think, let me go over the whole problem set and then you can try to finish in your own pace, but please let me know if you need any help. Otherwise people don't need to sit for the next one. Anyway, so what's the next one? Yeah. So what we want to do is like, the next problem is solving a XOR task with MLP. What do you have here? MLP means multi-layer perceptron. So we see hopefully soon that the the problem one is not a solution for XOR, so it cannot be linearly separable. So you have to have multi-layer perceptron. And what does that mean? So you have another layer, at least in the middle, which we usually say as call as hidden layers. And here in this case, I think there are 3 hidden layers. And then you solve basically the same thing. So you try to solve the problem of XOR. And yeah, you start with initialization and then forward layer, which is basically the training. And then to the backward propagation where you try to find the derivatives. And then finally update the weights, which is basically also ultimately, hopefully, we use these weights and see that the model is able to perform the task of XOR. Along with that, you also need some activation functions. For in this case, I think you use both the ReLU and the sigmoid ones. Exactly, and still the second problem. So you do them separately. So the first one is here, I think you use the ReLU, and then here you do the calculate the loss, and then you use the sigmoid. So basically, I think for the hidden layers in the bindle, you use ReLU, and for the final layer, you use sigmoid function. And finally comes this here, the part of MLP implementations, where you also fill up basically the same points, like this dot parts. I hope that this is easy to understand given the commented lines, which actually suggests what you're supposed to do. And then, okay, yeah. Then you finally finish with evaluation. The third task is do basically the same thing what you did for the second one, but here you use the PyTorch. Why do you use that? Because it's much easier. Did any of you actually work with PyTorch before? Okay, some of you did. So I hope that it's easier. Basically, these are, to understand PyTorch, I would suggest that you start with documentation of the PyTorch, which is easier. I think if you go to the link of documentation, if you need that, I can also send you that. But yeah, it's easier to understand what methods does what and what kind of inputs and outputs they take. I mean, dimensions they require. And basically you start doing the same thing. So you initialize. Here you also need to write how you calculate the binary cost entropy, which is a loss function, and then the optimizer. And you continue with the training part. Basically, here you have to define the data in the beginning, and then you have the training loops. For this case here, if you see, this means like, this wants you to actually print out the weights and to see what happens when you actually, after the input layer, and then before calculating the loss, basically before, after the backward. So basically this is the case. I mean, when you do it, I think it would be easy to understand, also easier for me to explain. And then again, finally finishes with evaluation. And the last problem is not with XOR, but basically now a real task. For example, not real task, I would say, but it's maybe give you more an idea of how kind of applications works. Real life applications, I mean. So here you are given the iris data set, and you have to perform the task of MLP. What you have in the data set is 150 samples of 3 species of iris. Iris is a flower, by the way. And what you're supposed to do is you have to actually predict which, so how many of the instances belongs to which species, basically. So you have to classify into these 3 categories of iris. And this is exactly also an MLP task. And then you go through the same things same process, basically like loading the data and then also defining your network and performing the forward function, backward functions and updates. So you perform the same things, but of course you have to change something. There are always some little differences in each of the tasks and the setups. And then finally, I think you would finish today's practicum. So this is a brief overview of what to perform or what the tasks are. Yeah. Feel free to ask any for help if you require. I go to the task 2. Yeah. Is there any questions so far? Hello. So let's go over the solutions. So basically what I'm sharing now is the solution part of the practicum today. And what you were supposed to do was implement, the first problem was implementation of a perceptron, and you solve the problem of XOR, of course. And you create a class here, and this class basically has kind of 3 functions. One is the forward pass, where you actually calculate the forward propagation, and then you upgrade the rule, basically you do the backward as well. And yeah, and in order to call these functions, you have to go through the training function and finally the inference. So what you do is you have your input data here, and the input data are these 4 instances where both of them are 0, 0, 1, 1, 0, 1, 1. And the targets are as well, you specify them as a vector of 0, 1, 1, 0. And then you call the train function of this class, where you send both the input data and the targets basically here. And then you perform then the forward pass, which is basically also here, this function. And you already know the formula, which is basically x into, so the input into the weights plus bias. And basically you just do the same thing with NP dot. The next thing that you do is that after you perform the forward pass, you also have to update the perceptrons weights, basically. So here, then we call this perceptron update rule, which is another method here. And then what we basically do is you add up the loss multiplied by the learning rate and y add. So basically, if you need to reduce, I mean, if the weights needs to be reduced, then this would be minus, this whole thing would be minus. And then you can reduce the weights. And in case this is something that you, the weights need to be increased, then this part would be positive. And then you can actually update the Newton weights likewise. So, and you can also check the inference, check the learning of the model or the perceptron transfer in this case. And here you see that, I mean, if you do it multiple times as well, you will always see that it cannot give you an appropriate answer. So that accuracy is, I think, for the most of the cases, it won't be what you expect. And for this case, it is around 25%. Which is basically the last one is correct, all the 3 other are wrong. Yeah, here is actually what is very finding it out, so you can see. Here for the accuracy, you don't need actually the threshold for this case because the outputs are already binary for a perceptron. But yeah, we actually follow the same things for the rest of the problems. So it's a good thing that you already need to know that if you specify a threshold of 0.5, anything higher than that would be considered as output 1, and lower it would be 0. So considering that, we see that the accuracy is kind of 0.25, which is not what we want. So how can we solve this problem with NLP? we start by do not a random initialization, but Xavier initialization, which is a good practice, let's say. But of course, random initialization would also work. But you start with that, and again, you have likewise the feed-forward layers class where you have the functions, for example, the definition, the methods for forward, backward, and where do you start? You have what you need here is a few activation functions as well. So for this case, you also have the class of relu, and we will need this but let me come back to it. That's just what you need for to do this task. And then the binary cross entropy loss, the segment functions as well, and here the implementation starts. So you have the data again, and what you do is we have an MLP implementation class, and we specify what we need. So if we have an input size of 2, output size of 1, hidden layer of 3, likewise, and the input data and the targets are similar because it's an XOR problem. So we specify that, and then what happens here in the class is you make it easy accessible for all the methods in the class. So you actually take whatever you actually gave to the class and do the self dot of it, and initialize the hidden layers. What does that mean? So you have to specify the dimensions. For the layer 1, the input size and the hidden size are different. I think this is 2, right? Yes, and the hidden size would be 3. Sorry. And we go to that again. And for the rest of the layers, where the hidden size and the hidden size layers, which is probably 3 and 3. So you have to specify it differently. And for the output layers, it would be 3, 2. Or 2, 1, sorry. And similarly, you have the forward pass and the backward pass. The forward layer pass, you do the same thing again, but for each layers, so the linear transformation is the first one. So, and then you calculate the activations, which is for this case, ReLU. And for the final layer, you do the linear part, so linear transformation, and finally you do the you use the sigmoid activation functions. You perform the backward derivatives, and then so you have to do the reverse dot layer. I think this was the questions, right? As well. Wait a second. Or it was already given. Just look. Yeah. Yes. Okay. And then, so basically you start with the training. So you call the train method first. You calculate the forward pass, similarly as we did for the previous one. And then you have to calculate the loss function. And then you have to do the backward pass and finally update the values. Okay, in the inference, what we do is you don't do the forward pass, of course. I mean, you don't need to update the values, but what we do is just give an input and see that output. Okay, sorry, is there any questions regarding this? Yes?
Will these solutions be uploaded?
Yes, uploaded. It would be uploaded. Any other questions? I mean, yes?
About the first exercise, we don't update the bias. If we will update the base.
Wait a second. You mean
If I have only zero update rule,
the update rule? Am I in the right place? Wait a second. No, it's not. Down, it's down, right? Wait. Where is it? But you mean the second question or the first one?
exercise one, the update rule, the way you define the class.
Yes.
That-
Yes, here. Yeah. Yeah.
So we don't update the bias, we just update the weights.
Yeah. You don't update the bias because it's a constant, right? Huh? It's a constant. It's a constant, right? So bias is always a constant. It's used because what you don't want is to get a zero. So basically, you always add one. You don't need to update the bias because it will always be constant. It will be always zero. When you do a derivative of bias, it would be always zero. I think. Am I right? One. Sorry.
The gradient of bias is zero, right? Because
You're ready? Yeah.
and then you don't need to update.
Okay.
I
Yes.
think you better understand, like, you update the weight that like the influence of the bias, right?
Excuse me, can you repeat it?
Like, you also have a weight for like the influence of the bias to a node. So you
Yeah, exactly.
somehow
Yeah.
do like update it.
Yeah. So
But
yeah.
that's the weight, not the bias.
Yes. What we want to do is like we need to update the weights as well. Anyways. Okay, here again, so basically it's the same thing. And this I did already. And the third problem is doing again the same thing, but using Python. So you use Python methods for this. And for the first case, you do, so basically defining the model, you have to define the weights of each layers, and you do as done here. And then you initialize the weights as well. Yeah, and basically these are all the functions, but what you do is you start the training down below. Wait a second. No, sorry. Here, so you define the data again. You start here, and then you start the training for each epoch. So you have now go through the 3,000 epochs. For each cases, you print the weights, and you see that where the weights changes and not. So if the epoch is less than 2, then you find the weights and the gradients of and see what's the changes, what's the output. And then here again, you print the loss. Sorry, this is actually for me also confusing. Wait a second. Yeah. So these are the value after forwards, and these are the values after loss calculations, and these are the values after backwards. And you can see the changes in their weights, and you can see only after the updates, the weights changes. Before that, the weights actually doesn't change. So you can see it from here as well. If you look into the outputs here, you see the weights are actually same. Then you go to the evaluation part again. So what you do is you want to evaluate the model learning. And basically you see now there is a learning of 0.5, which is okay. I guess it would get better later on. But anyway, that's how you evaluate basically. So you call again the accuracy, and you pass the predictions and the targets and the threshold of 0.5. And finally, yeah, you can print it out. The final exercise was iris data set. And here, what you need to do is you first try with using GPUs instead of CPU. And the instructions were given here how to do it. I hope that you tried it. And then you load the data set. And as mentioned in the instructions, the number of classes are 3. You split the data accordingly. So basically you have the train, test, and the label. So basically these are the instances that you use to train, and these are the labels. The Y are the labels. And then what you do is these are all the sensors that you need to make in order to work with. Then finally, here again is the definition of the model. So basically you have the layers and the dimensions of each layer and what kind of activations you use. And then you calculate, you apply by source and calculate the loss. And then again, the stochastic gradient descent. So basically what you do now, again, you run over the epochs. You find the output of using the model that is defined previously. And then the loss functions by just the output and the training labels. I mean the correct labels basically, and then perform the backward basically, and then use the optimizers, so which actually updates. Performs the actual weight updates based on the gradient computed during backpropagations. This is actually done in CPU, so you don't use the tensors, I think, here. And this shows how the time differences is. So when you use the data lake loader and the GPUs, I think it's written here as well, before the execution time with and without the GPU and batching. So when you use batching is like what we do with the data loader. And without the GPUs, it actually takes kind of higher time. It's here, and here you see it's kind of reduced to a lot. Then finally, of course, you evaluate, and you can see that evaluation score now is way lot than what we had before. The final part was to find to understand what this confusion matrix actually says. Did any of you figure out what does that mean? Like how to actually understand this? Okay, so what it means is like how to read this. Basically, if you go through the column is exactly what the actual labels are, and by row wise, it's actually the predictions. So for this first one is for the first class, let's say. So the first one would be, so 16 would be the number of times the model actually predicted the class, which is correct, which is like exactly 16, and it didn't make any mistakes. So the predictions are also 0, and the actual is also 0 for this. And for this is for the second class, where we have one mistakes. I think it's one wrongly. Wait a second. It's a false positive or a false mistake match. It's not here, but anyway, so there is one mistake by the model, and here as well. So this is one wrong. So in that case, that's actually how to read the model. So this is for the number of times the model and the true labels are like similar, basically, which is most of the times correct. Anyway, that was it for today, and hopefully, some of it makes sense for you, or you understood something. If you move out my confusions part, but anyway, the solutions will be uploaded as well. So thanks for coming to me. Let's stop.
Yes. Talk about that, brother. Sorry, can I ask one more question?
Yes.
How did you get the number 768 or something?